I think Walter wants to record. Is it okay for you, Andreas?
Okay. As the less jokes then.
Well, okay. Welcome everyone to this seminar. And this afternoon we have Andreas Thom on asymptotics of Cheeger's constants and unitarizability of groups. Please, Andreas.
Yeah, thank you very much for the invitation. And I apologize to some of you that might have heard me talk about a similar topic maybe already, or similar talks. But anyway, so what I want to talk about is the asymptotics of Cheeger constants and unitarizability of groups. So it's in between function analysis, representation theory of non-commutative groups, and also their geometric study, so geometric group theory. And so the rough outline of the talk is I will first very quickly remind you of amenable groups, and then the space of Littlewood functions. So that's the main tool that I want to use to study groups and define some characteristic invariant of a non-commutative group that we think is very interesting. And it captures some aspect of this problem of unitarizability of groups. And I will also talk about that, introduce that. And then later we will come to a really interesting in-between case of a group, which is, well, it behaves a little bit like an amenable group, but in fact it's not amenable, but this intermediate case is really interesting because it hints to like a route towards the construction of maybe a group which is unitarizable but not amenable. And so all this is joint work with Maria Gerasimova. She was a PhD student in Dresden, Dominic Gruber and Nicolas Monod, right? So it's joint work with them. Right, so amenable groups, I think I don't have to say much about, but since there are some technicalities that will be important, I will go through the definition. And so a group is called amenable if for any subset of the group and any epsilon, there is another subset. So as the subset was finite, there's another finite subset, so that the boundary of this finite set with respect to S, the set you started with, is small compared to the set F. And by boundary here, I really mean what's called the edge boundary in the Cayley graph. So it's basically all the pairs of points, an element in the set F and an element S in the generating set that leaves the set F, right? So it's what you think of as the geometric boundary in terms of the edges. And it's well known that solvable groups are amenable and non-abelian free groups are not amenable, right? So you know that. And a different characterization of amenability in terms of more like a more functional analytic characterization is that of the existence of an invariant mean. And that's just a, unital function positive on L infinity gamma, which moreover has this property that it is invariant under the natural shift action on L infinity by the group. So it just shift, and well, you want that this doesn't change the value of this functional, right? And you can think of this really as some sort of an integral of that function with respect to some measure. So that's like intuitively what you would can think about it, and it's invariant. And so the finitely generated groups from this perspective, they fall, I mean, that's my picture of this zoo of finitely generated groups. And so they have this large ball of amenable groups, and they consist of like smaller balls of groups that are amenable for a specific reason. So they're elementary amenable groups, solvable groups, nilpotent groups, abelian groups, finite groups are all amenable. And then there is an outside world of groups which is less kind of hierarchically ordered, but certainly the ones that are the most non-amenable, these are the ones that contain a free, non-abelian free group, right? So these are groups that are, for like one could say, for an obvious reason, non-amenable. But then this class is really larger, and we will come to that, and somehow this intermediate area of non-amenable groups that do not contain a free subgroup, that leads to interesting questions. So famous examples are the Burnside groups of large exponent. So these are finitely generated groups. All elements have the same finite order, some prime number large enough. And these are known to be non-amenable by the work of Adian. And it's, for example, an open problem whether such groups also exist in the amenable world, right? So is there a quotient, for example, of this universal one, which is amenable but not finite, let's say, right? And these non-unitarizable groups, they are also kind of in between this I mean, the interesting non-unitarizable groups are in between these two classes, the amenable and the ones that contain a free subgroup, and we will talk about them. And so the aim of this entire lecture is to construct a numerical invariant that kind of goes like here, right? So it takes the value infinity here, and it takes the value 1 here. In fact, it takes the value 0 for the finite groups. And then there are lots of question marks for the intermediate ranges, but it's some numerical invariant that you can associate to just just a group, let's say. And it doesn't depend on the generating set or anything. It's just a numerical invariant defined for a group, right? And well, we study basically its properties. And so that will be this Littlewood exponent that appeared in the title of the talk. But let me start slowly before we come to this Littlewood exponent and talk a little bit about uniformly bounded representation. So I'm studying linear representations pi of a group gamma on a Hilbert space. And these are from the start, they are not necessarily unitary, right? So that's the setting in which I'm working. So I study representations on a Hilbert space, not necessarily unitary. But such a representation, it is called unitarizable if it is conjugate to a unitary representation, which makes it kind of a trivial thing to, I mean, if unitary representations are known, then you can just now conjugate to get all these that are unitarizable. But okay, that's just the motivation. But we observe that such a representation is automatically uniformly bounded in the sense that the supremum over all the group elements of the norm of this representation now is, of course, finite. And the reason is very simple. Well, if it is conjugate to a unitary, then you can just estimate the norm independent of the group element G, just in terms of these elements that conjugate your representation to a unitary representation. And the main question that we wonder about is the converse. So is it true that if you start out with a uniformly bounded representation, so one for which this supremum that I've written is finite, yeah, if this is finite, is it automatically unitarizable? So is this the only reason why something like this could happen, right? So that's a basic question. It's very old, dates back to the 40s and 50s. And before we come to that, let's just look at the finite dimensional case to see that, well, there everything is very easy. And in the finite dimensional case, a bounded subgroup is always conjugate to a unitary group. And the reason is the following. So the proof consists of various steps. So if the group is bounded, then everything is finite dimensional. So it's pre-compact. The closure is compact. Every compact is contained in the maximal compact subgroup, and then you can conjugate it to a standard maximal compact group, which you know is the unitary group. So these are all conjugate. Right? This is one argument. You could also use existence of the harm measure on a compact group and integrate. So that would be I mean, there are various approaches, but I mean, seeing this proof, it's very natural to wonder what happens if n is infinity, because various steps just do not work, right? So for example, the pre-compact is just not true, right? If it's bounded, need not be pre-compact. And the other steps are they are also not so clear. Okay, so let's start very simply and just think about finite groups for the beginning. And I claim that a finite group, even if it acts on an infinite dimensional space, of course, it is unitarizable. And the proof is a classical argument that is used in representation theory all the time. You just average over the inner product to make the inner product you started with invariant. And then since it's just an average, that's still the same topology, the same Hilbert space, and then everything is conjugate. So the first, that was that's known for like 120 years at least. And the first, in some sense, non-trivial situation is this theorem by Söckerfall v. Notch from I think the 40s, which says that if you have an operator T so that it's invertible and all the inverses, power of the inverses and powers of it are all bounded by the same constant, so this constant is finite, then T is actually conjugate to a unitary operator. And that exactly says that the group of integers has the property that all the uniformly bounded representations are conjugate to unitary representations, meaning that the group is unitarizable, right? That's kind of the first non-trivial case. And how is that proven? Well, you construct an operator Sn as the square root of this like average of powers of your operator T. And you consider a weak limit point of this sequence of operators. Take some ultra filter or take some limit point, and then it's very easy to check that this conjugate is unitary. So that was the proof. Of course, it looked longer when it was written, but seeing that proof, you immediately notice, well, if that works, then this should work for amenable groups just as well. And in fact, this was noticed by a few teams kind of independently shortly afterwards. And that's the theorem, the next theorem. So amenable groups, they are also unitarizable. And I give you now a slightly different proof, which is, I mean, it's not much different, but the proof goes as follows. So you have a uniformly bounded representation of your group. The group is amenable. And then you average, you first of all consider the following function that sends G to the square of the norm of its action on a vector. And then you take the mean and take the square root of it. So that defines a new norm. And because it was uniformly bounded, it's easy to see that it's equivalent. And it's also easy to see because of the invariance of the mean that it's invariant under the group action. But then it's also true that it is actually a Hilbert space norm, this average, just because the parallelogram identity gets averaged, right? It's an identity, and if you take the mean of all these shifts of the parallelogram identity, which involves just the squares of the norms, then again, that's again satisfied. So it's a Hilbert space norm. And as I said, it's equivalent, right? And then well, it's essentially the same argument as the previous one, but it's kind of looks a little bit different. So what Dix-May asked, and it's a very prominent question, are all unitarizable groups amenable? So is amenability the only reason why this phenomenon occurs, that all the uniformly bounded representations are conjugate to unitary representations? And at the time when he asked the question, it was not even clear whether there would exist one non-unitarizable group. So it was kind of before, like what we now say, obvious examples were produced. So Dix-May asked this question, and at this time it was even less known about this problem. But there are various constructions, particularly the work of Kunze and Stein, and also the Kunze and Stein was about SL2R. But later there were very explicit constructions of uniformly bounded non-unitarizable representations by Pitlick and Schwarz. And so the free group on two generators, this is not unitarizable. And then there is some sort of an induction argument showing that as soon as you contain the free group on two generators, it's also not unitarizable. You can basically just take your representation, uniformly bounded, not conjugate, you induce it, and then you, if that would be unitarizable, then you can restrict back and so on. So it's not complicated. But right, so this was in the 50s, and by the time it exhausted all the examples of non-amenable groups. So there was a positive answer for all the examples that were known, and the first task to tackle Dix-May's question would be to produce at least some examples of non-amenable groups that would not contain the free group on two generators. This was an open problem for some time until Olshansky constructed, using cancellation theory, the first examples. And then also, of course, these Burnside groups were shown to be non-amenable by Adian, but that was a little bit later. Now, the first examples of non-unitarizable groups that would not contain the free subgroup were Burnside groups. And this was shown by Nicolas Monod and Taka Osawa. And this was kind of the first thing that went beyond this class of groups that contained free subgroups. Right. Okay, let me skip this question. And well, let me now talk about the space of Littlewood functions, and then I will explain why it is a useful invariant to study this question, and also a useful invariant in general. So the space of Littlewood functions, it's called T1 of gamma. Well, first of all, it's a space of functions on the group with complex values. So you can think of this really as a space of functions on the group. And it's a little bit funny to define, well, because it involves some interpolation of two Banach space norms, and I will explain you how that goes. So first of all, a function in one variable on the group, it defines a kernel on the group in two variables, an equivariant kernel, right? So f of x inverse y. And this kernel, it might be the sum of two kernels that depend on x and y independently. So these are no longer equivariant, these kernels. And we say that a function f is a Littlewood function if this equivariant kernel can be decomposed into two kernels, so that one is bounded as a convolution operator from L infinity gamma to L infinity gamma, and the other one as a convolution operator from L1 gamma to L1 gamma. So this is like a sum supremum over the sum of absolute values. These norms are not complicated to write down. I didn't, but these are dual to each other. The one is mapping from L infinity to L infinity, the other one from L1 to L1. So these are kind of like the transpose of each other, these norms, in terms of the kernels. And so the space of Littlewood functions then has a very natural norm, which is given by the infimum over all the possible decompositions. So that's why I said it's interpolation. Oh, I know that Marek is in the audience, so he will correct everything that I'm saying incorrectly. Right, and now there are a few applications. So why is it related to interesting properties of the group? So first of all, it's always true that L1 gamma is contained in T1 gamma. So that's it's not complicated to see. But what is interesting is that Wysochansky showed that this equality actually characterizes amenability. So whenever a group is non-amenable, the space of T1 functions is actually larger than L1, right? And let's look at the free group, because the free group is kind of on the other side. So that should show a completely like the other extreme of behavior. And let's consider the free group on n generators, A1 through AN. And let's take f to be the characteristic function of the generators and their inverses. And what is clear is that the p norm of this function is just 2n to the 1 over p. And I claim that the T1 norm, so the norm in the space of Littlewood functions, is bounded by 2. And so that means, so if I mean, the first fact was obvious, but the second fact, I have to argue for that on the next slide. So give me some minutes to explain why that is true. but you see from the fact that Fn is contained in F2 using, I mean, that's true, but you have to use some more arguments. You see that this implies that T1 cannot be contained in LP of F2, right? So these, because kind of there are functions that are like bounded by 2, all of them, but they grow in every P norm, right? So, and that's why it cannot be contained in LP. And in fact, the same holds for any group that contains the free group on 2 generators. Right, so that means we're really on the other side. So it's not equal to L1, but it's not even contained in LP for any P. So it's much bigger, right? In fact, one can show it's not even contained in C0, right? It's even bigger than that. So why is it true that this was important that this norm bound? Why is it true? And so let me explain this, because it also tells you how this decomposition of the kernels is actually something useful in the computation of the norms. So we take the free group on 2 generators. So then this characteristic function, it is giving you an equivariant kernel, and the kernel is essentially this Markov operator that shifts in the, I mean, it just distributes the value in all the possible 4 directions. That's what it does, right? And now I'm considering a decomposition of this kernel. I mean, I have now basically one contribution for each edge in the KD graph, and I'm breaking the symmetry because I can kind of look at an edge either points towards the root or it doesn't, right? And if it points towards the root, then this would be the unique neighbor in that direction. And if it points away from the root, then there are 2 other neighbors that point also away from this edge. And this decomposition is not, I mean, it's not used for the first time here, allows you to break the symmetry, and you can define this operator F1, which would now, I mean, this would shift the values of the function inwards. Let me think. No, it shifts the value of the function outwards, of course. So it shifts one value to the 3 other neighbors. And this value of this function, of course, it doesn't increase the ad infinity norm. It just puts one value at 3 places now, but that doesn't change the ad infinity norm, right? Only that you have more places where it takes that same value. So this part of the kernel has norm bound 1, and its transpose, which would shift inwards, then has the same bound on the L1 space, right? And so all in all, you obtain that this decomposition gives you a bound of 1 + 1, which is equal to 2. I mean, just in case there are any questions, just interrupt me. So I think it's if you have.
I only would like to say that this was discovered by Professor Leiner in Heidelberg in 1970. That decomposition.
Okay,
it was
thank you
very
much.
important in many. So
yeah,
I see
used a lot. I mean,
so
this has been
probably he remembered this time also, 1970. Professor Leiner, yeah.
And so what I'm now defining is the Littlewood exponent. And the Littlewood exponent is now the infimum over all the P's, so the T1 is contained in LP. So it kind of measures how large this space of T1 functions is. And so we already know a few results. So for example, if the group is finite, then there's no restriction whatsoever. If the group is amenable, we know it's actually exactly equal to L1. And our theorem in this situation is that this happens only if the group is amenable. And there's a little step missing, because the infimum could be equal to 1 without actually having that T1 is contained in L1, right? Could be contained in LP for any P bigger than 1. So that's why there's still something to prove in this second step, right? And so the most interesting, I mean, one of the interesting results that I'm listing here is that there's this relation with unitarizability, because if the group is unitarizable, then the Littlewood exponent is less or equal than 2. And that's essentially a result of Božeko and Fendler. So I will also talk about it. But that's the relationship to unitarizability. Kind of on this path from 0 to infinity, you have amenability sitting at 1, and then there's something happen less than 2, and then you go to infinity. And we are really lucky, I think, that we were able to prove the existence of a group which is really in between the two extremes, right? Because most of the time, this dichotomy is kind of so drastic that you fall into amenable or non-amenable, and then there's nothing kind of, I mean, it's hard to measure this passage somehow. But there are really groups that do have this property that their Littlewood exponent is in between 1 and infinity. I already said that it's infinite if it contains a non-abelian free group, but then that's not necessary. There are also torsion groups that have this property that the Littlewood exponent is infinite, right? So there's, at infinity, there are some more groups than just the ones that contain a free subgroup. And then there are these interesting groups in between that have a Littlewood exponent between 1 and infinity. So we don't know if our example has a Littlewood exponent less than 2, probably not. But that would be kind of the place where we would start looking for potential examples of these non-unitarizable groups that are still not amenable. Right, so that would be okay. Okay, so let me, So let me just, so that was this first step. So I will now basically, for the rest of the talk, I will say a few words about the proofs of these results. So what we need for this, and what is still missing in order to prove, I mean, something like more in the direction of this Dix-May problem. And so the first result was that Littlewood exponent equal to 1 actually characterizes amenability. And as I said, this result of Wysochansky says that being exactly L1 is a characterization, but a priori it's an infimum. So as I said, it could be contained in LP for any P bigger than 1 without actually being equal to L1 a priori. And so what we are using here is the following result of Ropoulos, saying that you can bound for a function that has positive coefficients or non-negative coefficients, you can bound the T1 norm by the usual norm in the reduced C-star algebra, so from L2 to L2.
Andreas, sorry, there is actually a question in the chat by Alexander Fry. So
okay.
Can you ask it, or shall I read? Alexander.
I can read it.
Sure, I can ask.
Okay.
And so I just got confused because I mean, you mentioned like these examples before of unitarizable groups which happen to be non-amenable, like because of like the conjecture by Dix-May, if every unitarizable group is amenable, and then you said that there have been constructed these examples which are not.
No. I mean, maybe I didn't say it correctly. So what we constructed is just a group that satisfies this. And if we would be able to improve this upper inequality to 2, like just a group in between 1 and 2, then that would be maybe a really good candidate. But still, I mean, the implication in the result of Božeko and Fendler is not going in the right direction for our purposes. So if the Littlewood exponent is less than 2, it does not mean that the group is unitarizable necessarily. So maybe Marek is starting to work on it while I'm talking. But so that would be very nice if we would know that it's actually an equivalence in 2, and then this bound would actually help us to prove construct the counterexample. But I mean, both things are missing. Okay.
Okay.
Right. So we have this this inequality for functions with positive exponent, positive non-negative coefficient, sorry. And then there was a result that was useful completely independently, which was just saying that if you have a non-amenable group, then you have very large sets that have a very small spectral radius. So this was actually an open problem, whether a non-amenable group would have a generating set with spectral radius very, very small. So of course you can take powers of the Markov operator, the norm gets smaller and smaller, but you find one generating set that does this. And that was answered in a paper that from a few years ago, where we constructed, I constructed very explicit somehow generating sets that have a very small spectral radius. And this now in combination with this inequality can be used that to prove that it would not be contained in LP as soon as P is small enough in terms of this epsilon that exists here. So there's like a small gap around 1 for a non-amenable group, meaning that the Littlewood exponent it's really bigger than 1. So now we come to this. I mean, I didn't talk about Cheeger constants so far, but our main tool in proving the other results, or some of the other results, is a relation of this Littlewood exponent to a quantity which is completely geometric in terms of the K-D graphs of the group. So it's much more combinatorial, and then this we can actually control by techniques of cancellation theory of groups, right? So there's this huge theory constructing all these monster groups, and we can apply it to construct our personal monster that has this Littlewood exponent in the right range. Okay. So there is, let's say you have a finite generating set, then of course there's the K-D graph, and there's the Cheeger constant, and here I'm really taking the edge boundary, so it compares the edge boundary to the size of your set F. And the group is amenable if and only if the Cheeger constant is 0, and well, if it's not amenable, then something happens. And what is important for us is what we call the relative maximal average degree. And it's related, so that's this quantity, it's related to the Cheeger constant. But let me give you a more concrete description of it, which is as follows. So you have your K-D graph, and you start with a finite subset of vertices, and then you count all the edges that are inside this finite subset, and you compare that to the maximal number that you would expect, which is F times S. So that if all the edges would be inside, then you would have F times S. But now you only count basically, I mean, we call it the average degree because you average it with respect to the set F. And then it's also maximal because you take the supremum over all the sets F. So I will look at this very carefully on the next slides in a few examples so that you can get a feeling what this relative maximal average degree means. And so the funny invariant that we are constructing now in terms of this maximal average degree is a certain lim inf over all the generating sets. So we look basically at the worst case that can happen. And I show you on the next slide an example where we computed 2 examples. And then you see how these 2 formulas, so the definition of E and the definition of eta, how they work together. Okay, example. So here's the definition of E again. This is the definition of eta. And so 2 examples. So one example is that gamma is amenable, right? Then you take F to be a Fellner set, and then most of the edges that start in F, they will actually end in F. And so for this set, the number of edges is actually comparable to F times S. And hence this quotient here, this will be equal to 1. And then the logarithm of 1 is 0, and you obtain eta of gamma equal to 0. Okay, that was easy. And now look at the next example is the example of a free group. So if you have a free group and you take a finite set F, then the induced graph on the finite set, if you take the K-D graph is the tree, then it will be a forest, or let's say it's also a tree because that's the worst case. But then for a tree, the number of edges is comparable to the number of vertices. So it's 1 less than the number of vertices. So you see that this maximal average degree, like here, is actually S to the -1 because you're dividing by F times S. And so in general, so logarithm So this gives you then +1 in this formula, right? S to the right, if you take S to the -1 is +1. So the eta of gamma for a free cube is 1. So it's also some passage between amenability and non-amenability, but now in terms of like isoparametric properties of the graphs. And in general, if you want to understand this quantity eta of gamma, then it's really the interest. I mean, we are really interested in Cayley graphs and finite subsets, so that there's in an exponential way a positive proportion of edges that's running inside the finite side F. And in the amenable case, it's very extreme because it's almost all, and in the free cube, it's the other extreme because it's almost none. Most of them leave, right? And so this alpha will be really the quantity that we are interested in. So that's kind of the passage from 1 to 0 in this exponent. And our theorem relating it to the Littlewood exponent is that there is an equality of these two sides. So one is a formula in terms of the Littlewood exponent, and the other one is this geometrically defined quantity that we can hope to control by controlling the cube carefully on all the generating sets and so on, right? So this left-hand side allows to actually compute the right-hand side in interesting cases, right? So that's so, and it's really proven using, I mean, we really have to prove two inequalities. So it's not coming out of some abstract formula or something. It's really like this. Okay. Okay. This. Okay. So I will. In the end, I will tell you how this formula allows us to construct this cube with this intermediate Littlewood exponent. So this was one of the results that I think makes this invariant interesting. And if you read the formula, it exactly means that there is something here which lies in the open interval, right? So there exists gamma, where this value lies in the open interval, not at one of the extreme points, right? And that makes it interesting. Okay, but before I do this, I will also show you a quick argument proving this result of Božeko and Fendler, that there's a relationship between the Littlewood exponent and the unitarizability of the cube, because that was also interesting in our mind. And so what I'm proving to you is that if the cube is unitarizable, then, right, so that's, let me write the statement. So if gamma is unitarizable, then T1 of gamma is actually contained in L2 of gamma. Right, so that's what I want to argue now, and I proved this really. Božeko and Fendler proved it just for every function. I mean, element-wise, basically. Right? And so you start with a Littlewood function, so a function in this space here, and you can write it as a sum of two kernels which are not equivariant anymore, and one is bounded from L infinity to L infinity, and the other one is bounded from L1 to L1. And now what you look at is you look at the commutator of the left action of lambda with convolution by this operator F1, and because F1 was bounded from L infinity to L infinity, this commutator is now bounded from L infinity to L infinity. But what's important is that it differs from the other convolution operator, which is the one given by F2. It only differs from this operator here by an equivariant operator. So rho of F1 is different from minus rho of F2 only by an equivariant operator. So forming the commutator with the left action doesn't see this equivariant operator. And so you obtain that this is actually the same as the commutator with minus the commutator with the convolution by F2, which is now bounded by well, that's, sorry, what did I write? Yeah, so this is now bounded from L1 to L1, right? Okay, so you have you have the same operator bounded from L1 to L1 and from L infinity to L infinity, and that means that the Ries-Thorin theorem tells you that this is actually, this defines actually for each, this actually defines a bounded operator from L2 gamma to L2 gamma. Right, so let me, yeah, exactly. So for each group element, you get this bounded operator, and it's uniformly bounded because it's, everything was bounded by 2 or by 1 or 2. So this is and it's essentially given by a commutator, which means that it will satisfy this Leibniz rule, right? So it was satisfying it on L1, but now it's satisfying it also on L2. And so this Leibniz rule is very useful because you can use it. You can, so it's something like a cocycle, one cocycle, you can write it in the upper right corner to define a new representation on L2 gamma direct sum L2 gamma, which has this additional part in the upper right corner. And because it satisfied the Leibniz rule, this is multiplicative, right? So you get a uniformly bounded representation. And I mean, one can actually check that it is unitarizable, this representation, only if this derivation was inner. And having this allows you then, I mean, there are additional arguments to prove that this function f that you started with is in L2 of the group, right? It's essentially a matrix coefficient, which often, it's not quite in L2 then, but then an additional argument proves that it's in L2. Okay, so that was a quick outline of this proof of Božeko and Fendler proving that that this is contained here. So this proves that if the group is unitarizable, then the Littlewood exponent is less than 2. So what's the picture now? So we have, let me remind you of this picture. So you have here infinity, you have 1, that's Aminable. Then you have 2, and so somehow here on the left, you have these unitarizable groups, and then you have here the groups F2 and all the groups that contain F2. And now what is really interesting, is there anything in between, right? Right. Of course, I mean, on the other side, if we could show that there's nothing in between, that would be also nice, because then we would also prove the Dix-May conjecture. But okay, so we constructed something in between, hinting at a possible way of finding a counterexample, but who knows? And okay, now in the last minutes, 10 minutes say, I want to give you some outline of the construction of our group that has this Littlewood exponent in this intermediate range. Right, and so in order to construct, now I have some problem here. So are you still here? Yes. Yeah. Okay, so I have to start the app fresh, I guess. So at the moment I have the problem that I cannot write on this slide. Can I write here? No. Huh. Well, I guess, should I just continue without writing on the slides? Maybe that's the easiest, because otherwise I would have to, I don't know what to do now. Restarted the app.
Let's continue.
So was there the battery? Is there a battery problem on the pen that was suggested in the chat?
The battery problem on the pen, that's a good idea, but it shows 93%. this still works. I don't know what's going on here. Ah, okay. Sorry. Okay, so we want to have this group with this Littlewood exponent here. And so, okay, there was this quantity, which was this relative maximal average degree that was counting how many edges would stay inside a kind of want-to-be Fellner set, right? And maybe it's not all of them, but maybe it's still f to some alpha, so like an exponentially big proportion of the edges that stays inside. And this is exactly measured by this invariant, and then this is the relationship with the Littlewood exponent. So we're looking exactly for a group, and now it's getting complicated, so that for each generating set, that's complicated, right? For one generating set maybe, but for each generating set, that's complicated. For each generating set, there exists a finite subset F, so that if you take the induced graph on the finite subset of the KD graph with respect to S, then that contains exponentially large proportion of the edges that you could possibly see, right? So it's a weakening of amenability, but it's not as bad as the free group, right? And so we want this alpha to be positive and the group to be non-amenable, of course, right? Otherwise, that would be easy. And so how do we do that? So that's sort of this procedure that you may have seen in graphical cancellation theory, also how Gromov constructed his famous example. It's a procedure of consecutive taking, starting with a hyperbolic group, maybe a free group, and then taking consecutive quotients, and then you, on the way, you would ensure more and more bad properties, so that in the end, in the limit, it's still non-trivial. That needs sometimes additional argument, but it has accumulated all the bad properties so that it's really, really bad. And so what we want to do, we have this infinite number, that's a countably infinite number of possible generating sets of the group. And for each of them, like finite generating sets, for each of them, we have to construct like this set F inside. And so we construct it basically step by step, right? So it's an iterative procedure, as I said. And in each step, we introduce enough relations so that for one more finite set S, a finite set F exists with the desired properties. Okay, so that's, okay, I didn't write down anything concrete, but that's what is going on. And how do we do that? Well, we have our finite generating set S, and then we take a random S labeling of a suitable Ramanujan graph. So you take a Ramanujan graph. Ramanujan graph is an extremely good expander. And so it, first of all, doesn't come with any labels, but now you randomly label it with elements in S. And so what you get is now a very connected thing that contains a lot of labels from S. And now what you do, you enforce that this will be a subgraph of your KD graph. So you have already a KD graph of your group, and then you have this randomly S-labeled Ramanujan graph, and you basically amalgamate the two things together so that all the loops that exist in this Ramanujan graph, these are S-labeled loops, they are all also loops in the KD graph. And so the trick is that if you construct this random thing well enough, that with positive probability, what you're getting will not collapse to a point. In fact, it will remain a hyperbolic group, and this Ramanujan graph will now be embedded in the KD graph. And so the vertex set of this Ramanujan graph is now exactly the set F that we are taking, because by construction, it had a lot of S edges inside it, but also some that are leaving it now, because it's only S to the alpha that we are getting. But that's kind of the construction. So we use, somehow we use this idea of small cancellation theory in a different direction. So it was previously used to construct expanders inside, so things that expand a lot. but now we are using it in the other direction by embedding this Ramanujan graph, which is kind of, it's an expander in itself, but it still kind of contains a lot of internal edges because it's so well connected, being an expander graph. And so I think you have to believe me. And to be honest, I believe Dominic Gruber. I mean, I tried to check the proof, but this small cancellation theory is a theory in itself. So it's not so easy to dive into these ideas. And okay, so we made it work in this situation. Right, so that's basically what I want to say about the proof. I mean, there's a lot of details about this random construction, and of course the proof that you can do that step by step without running into problems. And then in the limit you obtain a limit group, and so this will be a quotient of gamma. So for example, if you assume gamma to be a hyperbolic property T group to start with, this quotient would also be property T. And then if it would in addition be amenable, it would be finite, but then it cannot be finite, because if it was finite, it cannot be, I mean, it's infinitely presented the way we constructed the group. So there's like some very formal argument in the end showing that this final group that you're getting is not amenable. And that's why you didn't kill everything to like go all the way to amenability, but you actually ended somewhat before that. Right, so that's the construction. And I mean, there are lots of open questions. Of course, it would be very interesting to find more examples of such groups. I mean, we can hardly control this Littlewood exponent that we are getting. It's probably very, very large. Would be very interesting, maybe the set of Littlewood exponents is dense. We don't know. I mean, that would be very interesting. In particular, it would be very interesting if it can get a value less than 2, of course. And then if it's not dense, which, I mean, need not be the case, maybe there are some restrictions. So for example, we would really like to know whether this interval from 1 to 2 is maybe a forbidden range for the Littlewood exponent, right? If that would be the case, if you could exclude this type of isoperimetric behavior, then all the unitarizable groups would be amenable. But okay, we don't know how to answer this question. And this third question I already mentioned, is this actually, this Littlewood exponent less than 2 is actually a characterization of unitarizability, so the converse of this Bourget-Kofentler theorem, which we also don't know how to answer. But there are some funny or some, like, I don't know, surprisingly looking relations between these problems that are not so obvious at first. So if the Littlewood exponent less than 2 actually characterizes unitarizability, which we kind of think is not implausible, then at least there's a little bit of a forbidden range. So there's some interesting interplay between these, between the possible values and the relations to the properties of the group. Right. So that's what I wanted to say. I thank you for your attention, and I hope maybe there are some questions.
Thank you. So are there any question or remark?
Maybe if it's possible,
Yes,
I have a remark about that last question about the exponential 4/3, because we have another paper with Gero Fendler about some sense Fourier analysis and Fourier series when converge. That is some sense that exponential appear. So maybe this is some connection. This is another paper where we would like show that for Neumann or sister algebra reduce of free group has a good property as a Fourier series, and maybe this is, so my feeling is maybe this is connected. So thank you for Andreas for such a beautiful explanation, and so thank you. And maybe we should try to, by the way, from historical point of view, as I said, Littlewood first example function was done by Professor Leinert, and then his student Gero Fendler used this to construct in his diploma thesis in Heidelberg that explicitly representation, unitarizable, uniformly bounded representation, and this is later published. I forced him, and he published in Colloquium Mathematicum. But in this time, I was in Heidelberg, and we work about this business. So this was problem of Professor Leiner. Still, maybe also Dixmier, he know this is related, of course, to Dixmier. Of course, the similar question is for LP. This Professor Pizier, also this, there is also kind of P Littlewood function connection with the multiplier, Hertzsprung, or completely of P multipliers for LP business. So, but anyway, maybe this is also a related topic. So thank you once more, Andreas, for beautiful talk.
Okay, thank you. And anything else? Any other question? Remark? Okay, we thank Andreas again, but before you go, I think Richard wants to make an announcement.
So thank you. So I was asked to announce there's another NCG seminar, North Atlantic NCG seminar, which runs on Wednesdays, so Wednesday 5 o'clock. And if you search Google for North Atlantic NCG seminar, you find it. So tomorrow there's a lecture by Søren Eilers on the general theory of graph group star algebras. So if you ever wanted to know something about graph group star algebras, sorry, graph star algebras, that's where you learn it.
Okay. Okay, so if there is nothing else, so let's say goodbye, and we see next week with Lisa Glaser. Okay. Bye, everyone.
Bye.
And thank you, Andreas.
Bye.
Thank you, Andreas.